Hi everyone, and welcome back to educator.com. In this mini lesson, we're going to go over the A+ Physics worksheet on kinematics graphing motion, and you can download that worksheet at the link below. Let's dive right in. Number one, a cart travels with a constant non-zero acceleration. So we have some amount of acceleration, a changing speed, a changing velocity, along a straight line. Which graph best represents the relationship between the distance the cart travels and the time of travel? So we're being given here distance-time graphs, and we want the one that shows a constant non-zero acceleration. Well, if you recall, the way you get velocity from a distance-time graph is to take the slope. So if I start over here, I start with a very low slope and I go to a high slope. That means we must have a changing velocity. A velocity graph that would probably look something like that if it were a velocity time graph. Here we have a negative constant slope, so we would have a negative velocity. Here we start off with a positive slope, so we would start up here for velocity. We have a zero slope, and over here it's negative. So we would probably have a velocity time graph that looked like that. And over on the right, we have a constant positive slope, so we'd have a constant positive velocity. But we want the one with a non-zero acceleration, and it has to be constant. Well, here we have a constant velocity, a changing velocity, but at a constant rate. The slope of this would give us the acceleration, which would be positive and constant. So purple, if that's our acceleration time graph, is a constant value and it's non-zero. So our correct answer must be 1. Or as you look at this, you could think about it from the graph that you have a changing distance over time, and the rate at which your distance is increasing. And it's increasing at a constant rate. So you could use that to solve it too. Regardless, the best answer there, number 1. Number 2, we've got a car on a straight road that starts from rest and accelerates at 1 meter per second squared for 10 seconds. Then the car continues to travel at constant speed for an additional 20 seconds. Find the speed of the car at the end of the first 10 seconds. Well, what we know when it starts out, it starts from rest, so our initial velocity is 0. It accelerates at 1 meter per second squared, acceleration 1 meter per second squared, for a time of 10 seconds. So for the first 10 seconds, we want to know the speed at the end of that first 10 seconds. Well, final velocity equals initial velocity plus acceleration times time. That's going to be 0 plus our acceleration, 1 meter per second squared, times our time, 10 seconds, v equals, which implies then that our velocity is going to be 1 meter per second squared times 10 seconds is just going to be 10 meters per second. So the speed of the car at the end of the first 10 seconds, 10 meters per second. Continuing on with the same story, the car on the straight road has the same story, but on the grid below we're going to use a ruler to construct a graph of the car's speed as a function of time for the entire 30-second interval. So at the end of 10 seconds, we know that our car was going 10 meters per second. So I can draw that on my graph, and then it continues to travel at constant speed for an additional 20 seconds. So that would be our graph of speed versus time. Number 4 says calculate the distance the car travels in that first 10 seconds. And there's a couple ways we could do that. You could take the graph and you could take the area under the graph, or you could use your kinematics. Since we're talking about motion graphs, let's take the area under the graph in that first 10 seconds of the graph. And the shape there is that of a triangle. So we had 10 seconds here. We had a maximum speed of 10 meters per second. So the area then of our triangle, which will give us the distance traveled, area of a triangle is 1/2 base times height. So that'll be 1/2 times 10 seconds times 10 meters per second, or 50 meters. And you could have also done that with kinematic equations as well. All right, number 5. A student throws a baseball vertically upward and then catches it when it comes back down. If we consider vertically upward the positive direction, so up is positive y, which graph represents the relationship between velocity and time for the baseball, neglecting friction? Well, when I throw it up, the moment it leaves my hand, it has a large positive velocity. And as it goes further and further up, it slows down, slows down, slows down. At its highest point, it stops. So partway through its path, it's going to have 0 velocity, and then it's going to come back down. Greater and greater magnitude, greater and greater speed, but in the opposite direction. So it's going to have a larger and larger negative velocity. The graph that shows this best is number 4. We could also look at this graph and say, well, if we wanted to know the acceleration, what would the acceleration look like? The acceleration is going to be the slope of that line, which the slope of that line is negative and constant. So our acceleration time graph, acceleration time, would be down here, negative, and that's actually going to be negative 9.8 meters per second squared, the acceleration due to gravity. What would that negative mean? Well, if we called up the positive direction, the acceleration due to gravity is in the opposite direction, down. So that negative is indicating the direction there. Let's take a look at one more. The graph below represents the displacement of an object moving in a straight line as a function of time. What was the total distance traveled by the object during this 10-second interval? Well, let's take a look and see what we can figure out. As we start here at 0, 0, and we go up through that distance, we've traveled 8 meters. Then we have no change in displacement there. In the next 2 seconds, we travel from 8 to 16 meters, so we travel another 8 meters. And then finally, we come back another 8 meters. But because it's distance traveled, that's the total amount of distance you're covering, we have to add that in. So our total would be 24 meters, and our best answer there, number 4. All right, that finishes page 1 of the worksheet. Thanks so much, and make it a great day, everyone.